Okay, so I think we can start. So in the last lecture, we started discussing about, or we rather, I should say, we started reviewing, we continued reviewing probability theory, prob and stat, and we reviewed a number of items. But what we started but could not complete is our review of probability distributions. Right? We started with Bernoulli. I told something verbally because we were short of time, and that's where we kind of stopped. So today we will start with distribution. We'll talk about few of the distributions, and then we'll talk about this transformation of distribution, and from there we'll talk about maximum likelihood estimation in action, how we can use it for solving a problem. I'll show you one problem on that. Central limit theorem and law of large number. So this is kind of the plan for today, to start with distribution, then talk about transformation of distribution, central limit theorem, law of large number, and MLE in action, more or less. Okay. With that, let us start, and let us start with the distribution. So in the last lecture, we started talking about PMFs, sample PMF, and we were talking about Bernoulli distribution, right? So let us repeat that part because we did it very quickly, and then we'll move to other distributions, right? So the thing that we discussed last time was Bernoulli's distribution, and the PMF or PMF, right? For Bernoulli, it's a discrete PMF. The PMF for Bernoulli's distribution is if xx is equal to p to the power x 1 minus p to the power 1 minus x, and then x will take value 0 and 1. So if you are tossing a coin, 0 is tail, 1 is head, 0 is generally failure, 1 is generally success. Okay. And then your p, that's the probability, so it's between 0 less than equal to p less than equal to 1. It's the probability of succeeding. That's what p is, right? X is your outcome, whether you are getting a head or tail, whether you are succeeding or failing. P is basically your probability of success. And everywhere else, obviously, it is 0. So I'm not writing that, but because x will only take the value 0 and 1, it cannot take any other value. So only at those two values, it's okay. So now the question that we asked, or I asked rather last time, was that how do we know this is a PMF? I mean, it's a function, but why is it a PMF, right? So why is it a PMF? It's a valid question to ask. And we know from definition of PMF that it has to satisfy two criteria. The first criteria is, what is the first criteria? It's bounded in 0 to 1. Non-negative is for PDF. 0 less than equal to fxx less than equal to 1. This is the first criteria. Now, given that x is equal to 0 and 1, p is between 0 and 1, everything is in power, this is trivially satisfied, right? This is satisfied in a trivial manner. So this is trivially satisfied given that p is between 0 and 1, it's in power form, x will take 0 and 1, right? So it's trivial. But that is not the only criteria. The other criteria is that sum should be equal to 1, exactly. So the other criteria is summation over x if xx should be equal to 1. If I have to do it for this, x takes the value 0 and 1. So let's take the value 0 first. So if I take the value 0 multiplied by sorry, if I take the value 0, then it is p to the power 0, which is multiplied by 1 minus p to the power 1, that will give me 1 minus p, plus p to the power 1, 1 minus p to the power 0, and this will give me what? 1 minus p plus p, which is equal to 1, right? So it's a PMF, we can verify, right? I also said that the mean is equal to p, and I told you how to do it, but let's do it. So expectation, right? Expectation of the random variable x we know is equal to summation x fxx. Now in Bernoulli, x will take value again 0 and 1. So let's write it down. So 0 multiplied by fxx at 0 is 1 minus p, plus 1. So x takes the value 1, success, and that is multiplied by p, probability of success, and you can see you will get p, right? If I have to find out the variance, we can do that as well. So let's try that. So if I have to find out the variance, we know that variance is equal to expectation of x square minus expectation of x whole square, right? So expectation of x square minus expectation of x square of that. Now the second term I know is p square. This term is p square because expectation of x is equal to p. The first term is what I need to calculate. What is the first term? It will come out to be p again. So the first term is e of x square, so that is equal to summation of x square fxx minus p square. Let's keep it. Now when you do summation x square x, you will get 1 times 1 square times p plus 0 square times 1 minus p minus p square. So you will end up with p minus p square, which is equal to p 1 minus p, right? And this is what I told last time, that you can find it out. It will come out to be p multiplied by 1 minus p. There is one more thing in Bernoulli I want to discuss, but I will not discuss now. Let me go to the other distribution and then I'll come back to that. And that is I will be demonstrating the MLE concept, the maximum likelihood estimation, in the context of this, because it's easy. It will take me less time, but it can be done for others also. So we'll do that. We'll look at how P can be estimated given some data, given some experimental data, using maximum likelihood estimation. We'll look into that, but we'll look into that after we have discussed some of the other important distributions. Now, what I'm not discussing is, for example, the Bernoulli is one trial. If you do n number of trials and look at the number of times you will succeed, then that will become binomial. I'm not discussing that because for this course, I think that will not be needed that much. If needed at some point, we will discuss at that point. Then what happens when you were throwing a dice? Because in that case, it is not 0 or 1, it is 1, 2, 3, 4, 5, 6. So in that case, Bernoulli will become multinovely, or categorical distribution also you can say. So multinovely. And then binomial equivalent is multinomial. Again, these are things I am not discussing. I'm only discussing Bernoulli, and now we'll jump to uniform. But there is binomial, there is multinovely, and there is multinomial. So Bernoulli is for one trial, or you repeat the trial, but you are only interested in outcome of that trial. Binomial is you perform the experiment n number of times and you are interested not in outcome of a trial, but in how many times you will succeed, how many times. Multinovely is like Bernoulli, but the only difference is that your outcome will have multiple, like more than 2. And multinomial is like binomial, but you have more than 2 outcomes. Okay, so these are the 4 very related kind of distributions. I just covered one, which is Bernoulli, just to give you an introduction. Others I will not cover. Okay, and we will probably not need it, but it is good idea to read those on your own, just to get. an idea, right? What is it? Okay, so this was Bernoulli. Let us go to the second, which is uniform distribution. Uniform distribution. Okay, uniform distribution you generally denote as using a calligraphic U. I mean, that's a common notation. I mean, and then you write what the variable is, and then you write in what range that variable is. The distribution is non-zero. So, or what is the bound of this uniformly distributed random variable? And generally, the bounds are denoted by A and B. This is how you denote a uniform random variable. So anywhere you see something like this, you know that that's the uniform random variable. Okay. Moving ahead. Now, what does the PDF looks like? The PDF looks like as follows: 1 by B minus A, and this is when x belongs to A comma B, and this is equal to 0 elsewhere. Okay, this is 1 by B minus A, the PDF, and yeah, 0 elsewhere. How does it look? You can see that the PDF value, non-zero PDF, is not a function of x. That means it is constant everywhere, which means it is uniform everywhere in that bound. That's why the name uniform distribution. The name comes from the fact that it is uniform. The probability mass is uniform for any given range anywhere. So how does it look? If I have to plot it, you take, let's say my range is, this is A, this is B, so it will be a constant probability mass or density in this case, and this height is equal to 1 by B minus A. This is how uniform distribution looks like, right? It's not a function of x. And less than A, 0, greater than B, 0. So it is non-zero only in that bound, everywhere else it is 0. So it's a distribution that have a I mean finite support or finite bound. There are distributions which do not have finite bound, Gaussian, we'll see, that's minus infinite to infinite. Uniform is not one. Uniform is having a finite bound. Okay. But first of all, why is it a PDF, right? Let's see if we can see so that it is a PDF. Why is it a PDF, right? What are the two criteria for a function to be PDF? Greater than or equal to 0. So first one is that f(x) should be greater than or equal to 0. Now in our case, A is the lower bound, B is the upper bound. 1 by B minus A will always be positive, satisfied, right? So trivially satisfied. This one is trivially satisfied. The other criteria is integration from my, okay, let me write minus infinite to infinite f(x)(x) dx should be equal to 1, right? This is the other criteria, that integration should be equal to 1. Let us do that. So if I have to do this, minus infinite to A f(x)(x) dx plus A to B f(x)(x) dx plus B to infinite f(x)(x) dx, right? Now can you tell me what is the first term equal to? 0, because f(x) is equal to 0. So this is in, I mean, we don't need to evaluate it, it's 0. The last term 0. So the only term we need to evaluate is this one, and that is equal to So what we are evaluating is a to b 1 by b minus a dx, uh, which is equal to 1. I mean, you can say that. I mean, I don't need to write that, right? So it's a valid PDF. You can prove it, right? We have proven it. The other thing is that what is the expectation? If you have to compute the expectation, we know how do you compute the expectation? Integration of x fx dx. Let's do it. Integration of x fx dx, and again you know that less than a will be equal to 0, greater than b will be equal to 0. So we will only do from a to b, and that's all we need. This is equal to fxx is 1 by b minus a, will come outside, x will become x square by 2. So 1 by b minus a, and then you have x square by 2 to b. Now if you substitute it, you will get b square minus a square by 2, which is b plus a multiplied by b minus a. B minus a cancels out. We end up with getting a plus b by 2, right? So that is the mean of uniform distribution. Everyone is able to follow? Simple calculation, nothing difficult. Okay. Variance, same thing we will do. Variance of x is equal to expectation of x square minus expectation of expectation of x whole square. Okay. Now the second term, again we know a plus b by 2 whole square, right? What we do not know is the first term, and we need to evaluate the first term, right? So let us follow. The first term is integration a to b x square 1 minus b minus a 1 by b minus a dx minus a plus b by 2 whole square, right? Correct. Now the first term 1 by b minus a will go outside, x square will become x cube by 3, right? So this is equal to 1 by b minus a, this will become x cube by 3 a and b minus a plus b by 2 whole square. X cube by 3 is bq minus aq. What is bq minus aq? Let us see. So this is equal to 1 by b minus a, there is also 3, so let's write like this, right? Yeah. And then you have b cube minus a cube, right? And then minus a plus b by 2 whole square. bq minus aq, what is it equal to? So this is equal to 1 by 3 b minus a, and this is equal to b minus a multiplied by b square plus ab plus b square plus ab plus a square, right? Yeah, right. Yeah. Minus a plus b by 2 whole square. This will cancel out, assuming b is not equal to a, which is obvious, otherwise there is no mass. And so you end up with b square plus ab plus a square divided by 3 minus b square plus 2ab plus a square divided by 4, right? Do the calculation, you will get b minus a square by 12. do the calculation, that's what you will get. B minus A square by 12. 12 you can see 4 and 3. B minus A square you will get. Do the calculation, you will see. 4 minus 6 will come. So that will make it minus 2AB. Because 4AB minus 6AB will make it minus 2AB, and that other things will 4 minus 3. Okay. So you will end up with something like this. So this is your variance. This is for uniform distribution. And you now know that if I give you an arbitrary distribution and ask you that is that a valid PDF, you know what to do. If I ask you that what is the mean, you know how to find. If I ask you what is the variance, you know how to find. And you probably also know, at least in theory, how to find the higher order moments. You might not be able to do the maths. I mean, it might be a little bit difficult, but you know what to do. At least if I give you a computer, you know what to do, given, right? So that's the idea. So this is uniform distribution. One more distribution I like to talk about, which is the Gaussian, obvious one, right? The most used one, okay, or normal as we call it, Gaussian or normal. Okay, and this is denoted as calligraphic n, the variable, and then the parameters. Okay, the parameters, and these parameters are your mean and variance. Okay, sometimes it is written mu comma beta inverse. That's another way of representing it. Mu comma beta inverse. So first of all, beta inverse is equal to sigma square. That is obvious. Second, what is beta inverse or beta? Beta is known as precision, which for Gaussian is inverse of variance or inverse of covariance also. If it is, we'll come to that. But for now, let's say it is inverse of variance. Okay. So how does the PDF looks like? Fxx Gaussian. So 1 by sigma. Actually, I don't need this curly now because root 2 pi exponential of minus x minus mu square by 2 sigma square. Okay, and here x varies from minus infinite to infinite. Okay, so this one is having infinite support. Remember I said that last one was having a finite support, a to b, these were finite numbers. For Gaussian, it is having from minus infinite to plus infinite. Okay, why is it a valid PDF? Well, this integration, I mean, to prove it a valid PDF, you need to prove two things. First is it is non-zero, which is obvious. Sigma is standard deviation, which is the positive root of variance. So sigma is always positive. Square root of 2 pi is always positive, and anything inside exponential is always positive. So this is greater than equal to 0. That's easy to prove. The other one is not so easy to prove because this integration you cannot do analytically. But if you do this integration and use some of the identities that are there, you can show that the integration will also come out to be equal to 1. And so it's a valid PDF. But that integration, for doing that, you have to use identities which have been proven, but analytically you cannot do this actually. So now you have calculator, so you don't need it. But in the previous time, right, even when I was doing, there was calculator, but still we were taught this. We were given tables of having the value of PDF for different values of x. So just like log table, we used to have a standard Gaussian table. Because you cannot do it analytically, so those values used to be given. That if x is this, then what is the PDF? Or actually not PDF, they used to give the CDF actually, because that's what we need for probability in most cases. So there is a standard normal table also that used to be done. Now you don't really need it if you have a calculator. Calculator has the function of evaluating Gaussian PDF by default. All the scientific calculators have it. But yeah, if calculator is not allowed, you need that table to do that. Okay. but it's a PDF because you can prove it, but not analytically by using identity. Okay. Now, because we are into the identity, let me write down the 3 identities that are generally used, right? So, and those identities are used to prove this. So, useful identities, I'll say. The first one is integration of exponential of minus z square by 2 dz is equal to, again, minus infinity to plus. Do you know what it is equal to? Square root of 2 pi. Okay. Okay. And then integration of minus infinite to infinite z exponential of minus z square by 2 dz. What is this equal to? This you should be able to tell. 0. Odd function, even function, you can use that. It will come out like that, but it's 0. And the last one is integration minus infinite to infinite z square exponential of minus z square by 2 dz. And what is this equal to? This is equal to square root of 2 pi. Again, the first thing will come back. Okay. These are the identities. Using the first identity, you can prove that 1 by root 2 pi, that thing will be equal to 1. Using the second identity, you can find out that the mean is equal to mu. Using the third one, you will be able to find out that the variance is equal to sigma square actually. Okay. Or in this case, expectation of z square is equal to 1, right? So this z variable I am talking about, right, is actually a is a Gaussian variable or Gaussian random variable with mean 0, variance 1. This is known as standard normal or standard Gaussian variable. So a standard normal variable with mean 0 and standard deviation 1 is known as the standard normal variable. Okay. So this z is actually a standard normal variable. Is a variable that is distributed in a standard normal, right? No, there is 1 by root 2 pi, right? Don't you think that will have a role to play? Because you have to find out the variance that will be equal to 1. Variance is e of x square minus ex whole square. E of x is 0. So if e of x square is equal to variance, which is 1. So 1 by root, there is root 2 pi is there, right? So that's it. That's okay. That's, we cannot do anything. Okay. The slides will be uploaded. They have to see side by side. I'm trying my best. All I can do. Okay. Okay. So these are the identities that you can use to prove certain things, right? Now, one more thing about distribution is that whatever distribution I talked about, the 3, are all univariate distribution. That means these variables will take one value, right? But in machine learning, it is rare that we will work with univariate distribution. We will always work with multivariate distribution, which means distribution of multiple variables together. That's the multivariate distribution. Let us also look at the multivariate distribution for Gaussian. Only Gaussian because that's what you will primarily need, but the same thing will hold for others also, more or less. Okay. So for now it is coming. You cannot do anything. For multivariate case, the PDF will look something like, you do one thing, just make the focus on me. ये slide बाद में दे देंगे. Multivariate case, if x, now this x is a vector, right? The PDF takes the following form: 2 pi, okay, x is a vector, so that it should have a number of elements. Let's say that number of elements in that vector is n, capital N. Keep that in mind. Okay, so x is a vector. Previously, that n was equal to 1. So that's why it was the univariate scalar. Now it is n-dimensional vector. So I have each x will have n entries. Okay, so 2 pi to the power minus n by 2 to the power minus half exponential of minus half x minus mu transpose sigma inverse x minus mu. This will be your PDF of Gaussian for the multivariate case. Now let us see if it is making intuitive sense or not, right? Let us see if it is making any intuitive sense or not, right? So let us see that. Effect 2 pi to the power minus n by 2. For n equal to 1, what will I get? Minus 1 by half, that is 1 by root 2 pi. That was the case earlier, it was 1 by root 2 pi. You can imagine, because there were n variables, it became to the power minus n by 2. Now there is sigma square, right? Now I have not yet defined, but that capital sigma is known as covariance matrix, where the diagonal terms are sigma square, sigma 1 square, sigma 2 square, and the off diagonal terms are the covariance. Now that means this matrix itself has information about all the sigmas, and I am taking determinant of that. Let us assume I have n independent Gaussian distribution. What will the covariance look like? Diagonal with the off diagonal term 0. And if I have a diagonal matrix, what is the determinant of that? Product of. So in that case, this capital sigma will become sigma I square, or square root actually, because there is minus half, and product of all of those, right? And that should happen. It should become product of this univariate PDFs. So this is happening. Now go to inside exponential. Now what did I have? X minus mu whole square, which is equal to x minus mu times x minus mu. In vector form, it is x minus mu transpose x minus mu. And then there was 1 by sigma square, small sigma square. That becomes capital sigma inverse. Now you can again assume that it is independent. If it is independent, you will see that it will become x1 minus mu1 square plus x2 minus mu2 square plus x3 minus mu3 square, and that will happen, which means it is exponential times exponential times exponential times exponential, which is like product of univariate ones. So intuitively it is making sense, and you can see so that if you have an independent variable, then this is actually equal to n times multiplying this thing. If you multiply this n times, you will get the exact same thing. Okay, I'll write one thing down. So sigma, okay, mu, okay, or maybe, yeah, mu now is a n-dimensional vector. It's not a scalar, it's a mean vector, because it's multivariate. And your sigma is a matrix, covariance matrix is what it is called. It becomes n cross n, right? And not only that, this sigma is equal to this sigma is equal to, how does it look? Sigma 1 square, sigma 2 square, sigma n square. So the variance term sits in the diagonal, and then here it will be covariance of 1 2, let's call it, or x1 x2 actually. So I'll write 1 2, which is like covariance between x1 and x2. and then the last term will be covariance of 1 and n. And then it's a symmetric matrix, covariance of 1 and n and 1 are same. So it's symmetric. This is covariance of 2 and n, and then you can write it. This is covariance of 2 and 1, covariance of n and 1, covariance of n and 2. This is how it will look. It's a n cross n matrix. Okay, clear? And again, similarly, do a multivariate integral, you can show that it is equal to 1, it is always greater than equal to 0, all of those things holds directly. Okay, so this is your Gaussian distribution. Okay, there are many properties of Gaussian. There are hundreds of identities of Gaussian. Convolution of Gaussian is a Gaussian, marginal distribution of Gaussian, joint distribution is a Gaussian, conditional of Gaussian is Gaussian. So all of this, for example, if A and B are Gaussian distribution, then A given B is Gaussian, B given A is Gaussian, A is Gaussian, B is Gaussian. And then you can also think about doing convolution of two Gaussians, that will also give Gaussian. It has various properties which we keep on using throughout machine learning and statistics in general, because it's really useful. Gaussian, in my mind, is called normal distribution because it is very common and normal among people. I mean, that's how I see it, because wherever you don't know anything, you assume things to be normal. It's normally happened. It's something like that, right? Obviously, there is a very strong reason in some cases, like the central limit theorem, for example, that dictates why you can take some things to be Gaussian, but it's the most used distribution, and the second best is some miles away from it. Okay. So yeah, so that is it for distribution. Any question on distribution? Any question, any doubt, anything you want me to repeat on the distribution part? If not, then let us proceed. Uh, Leave it, I don't have time. Uh, so yeah, so yeah, so this is it for distribution, right? Now next thing I want to discuss, which one should I discuss first? Let me discuss transformation of distribution. I like that very much, and that is actually something that is directly relevant to this course. So let us discuss transformation of distribution, and then we'll go to MLE. Transformation of distribution. Okay. So distribution is a function, right? So let us assume that I have a variable x which follows a distribution fxx. Okay. So suppose x or okay, this is not the correct way of writing it. Suppose x um, is a random variable with PDF fxx. Okay. So x is a random variable with PDF fxx. So what we do next is what? I don't see any bag here. Okay. So this is a random variable with PDF fxx. Okay. Now let us introduce another variable y, and y and x are somehow related. How it is related, I don't know, but it's related. Okay. So let's introduce another variable y such that y is equal to x square. Not x square, x square is very specific. Let's write it gx, right? We'll do x square later. Such that y is equal to gx, where g is some arbitrary function. It can be x square, right? Like the example I wrote, it can be 1 by x, it can be x cube minus sin x. You can imagine, right? So it is some random, not random, some function, but some complex function and some generalized function, but it's a function. And when x goes through this function, it gives y. So the question is that if this happens, what is the distribution of y? Because that's what we want to find out, and that is basically my transformation of distribution. Clear? The problem statement is clear. So I have some variable, it has some random variable, but now I do transformation on that. What is the PDF of the transformed variable? The obvious answer will be, okay, maybe you are thinking that I will put wherever there is g of x, I will put y, or wherever there is x, I will put g inverse of y, and that will be my distribution. That does not work in case of PDF. Why it does not work? Because remember, PDF has to be normalized. If you do g inverse y instead of x, it will not satisfy the normalization constant. It will not be a PDF any longer. The integration will not be equal to 1. So you need to satisfy the normalization property of PDF, that is integration from minus infinite to infinite should be equal to 1, and that constraint is always there. So you have to bring that constraint into picture to do this transformation. So how do you do it? So it is done very easily, but it is done through that constraint only. So let us see. So let's say this is the PDF of x, and for simplicity, let's draw something like Gaussian. Okay, Gaussian I did not draw. Gaussian looks like this, bell shaped. Okay, uh, and so this is my x, this is my fx. Okay. Now let's do also y. This is my y. This is my fyy. And just for the sake of illustration and argument, let's take fyy to be very complex. Very complex means, let's say it looks like it has multiple modes. Okay. So this is the fyy, and the only information I have is the PDF of x is known to me, and the transformation is known to me. These are the only things that is known to me. Nothing else is known to me. How can I use this to find out fyy? My objective is to find out fyy. Okay. So probability distribution has this nice property. The probability mass is conserved under this kind of transformation. The probability mass is conserved under this kind of transformation, which means I'm not talking about the total mass, that is obviously conserved, 1 and 1. But even if you take a very small dx, whatever is the mass of that should remain exactly the same when it becomes dy. That is the important part. So if I take a small dx here, right, this is my dx and this is the probability mass, right? I do a transformation of this mass, and who knows, maybe that will come somewhere here. Maybe that becomes something like this. Okay, because the scale of y need not be same, the scale can be different, right? And this is my dy. So this mass on the left should be equal to the mass on the right. When you do this transformation, for each of the small strips, the mass needs to be conserved. The mass will be conserved. That's the property of PDF, right? So if the mass is conserved, what can we write? On the left, what is that mass equal to? Let's say that dx is at a distance x. Fx dx, I can, because dx is very small, I can take it rectangular, as simple as that. So this will come out to be, this portion will give me f x x dx, and this is equal to what? Y dy, right? From here, what is my fyy? From here, my fyy is equal to what? Fxx dx by dy, right? But not only that, this also. Why? Non-negative. Okay. This is the transformation. I can also do some more steps. Dx by dy is there. What is x equal to? G inverse y. So I can write G inverse y and then do that. Okay. D dy of G inverse y. Okay. Using this, you can go, given that you know fxx, you know gy and g is invertible, or let's write it, you need to know the inverse, obviously. If you know the inversion, and then you can use this to go from one to another. You can also do the opposite, obviously, and do that. So that's fine. Okay. This is for univariate case. For multivariate case, what will change? Any guess? That will become the Jacobian, the determinant of the Jacobian, right? That what is modulus now will become Jacobian, because remember the Jacobian actually gives area, right? So that's where it is coming out. Okay, so it will become the Jacobian. That will, for the multivariate case, it will be del y del x del y, which is the Jacobian, and the determinant of that. Determinant of Jacobian is the area. We know that. Okay, so that for the multivariate case, that will be the case. Okay. Now you can use it to do different things. One of the main use of this thing in this course will be normalizing flow. Normalizing flow is one of the generative models we'll be discussing and spending significant time, 2, 3, 4, 5 lectures maybe. And that whole basis of normalizing flow is based on this transformation. The whole idea of normalizing flow is based on this. So we'll be spending significant amount of time, 2 weeks, 1.5 week kind of time, on just discussing this concept and how it is used in practice to design. Okay. Um, what do you mean by that? Dy is equal to g dash of x dx, obviously, but that has nothing to do with this. It has to be same because that is being inferred by this because of this constraint. What you are saying is the exact same thing I said does not hold, which is you cannot just put and say that they are equal. That does not hold. The area has to be equal is the constraint you have to satisfy. Other constraint goes out of the window. There is no other constraint here. There is only one constraint. The probability mass has to be constant. That's all. And so everything has to be determined from this. And how the area is same comes from the property of probability. It has nothing to do with y equal to gx. y equal to gx and dy is equal to that thing will hold for any function, but the probability mass being equal will hold only for PDFs. What you are saying holds for the function in general, but when you come to PDF, then it is all about this value of fy and fx. Because when I've written this thing, dy and dx are very general things. What you are saying will come automatically because fy will come out to be such value so that it gets cancelled out and it is same. It has to be same. There is no exception to that. And that's why the whole derivation is based on the fact that it is same. Okay. So you cannot look it in silos. Correct. What, no, it can happen in the sense that you are saying it's very small, that assumption will not hold, right? It will hold because it's like infinite, right? Infinite plus 1 is infinite. Infinite plus, so you are doing the opposite thing. It's so small that it will become small in that sense, right? So whatever is there will become small or it will become uniform in that range. Okay, so that will not have an impact. So I understand what you are saying, that maybe fy is so small that dy is becoming very large, but then it is not a rectangle, right? But that is very unlikely to happen until and unless you have a uniform distribution that goes from minus infinite to plus infinite almost. That is the case when you have, think of A and B, right? A and B being very far apart. That means each, I mean, everything is possible equally. That's the case you are talking about, right? So even in that case, it will hold because it's a differential element by definition I'm working with, right? That's the whole purpose of differentiation. Any other question? No, for this condition is satisfied not for fx and fy to be PDF individually. For fx x to be PDF, you know the property greater than or equal to 0, integration to be 1. Fy to be PDF, you know the properties. This condition is that for it to be a valid transformation. It is for the transformation to be correct. It has nothing to do with individually they being PDFs. Individually they can always be PDFs. But is that a valid transformation? You're saying something? Same. When you do this, it has to be same. And not the total probability, but the strip. Like whatever mass you take, that mass is conserved. It just means that you take a mass, right? Probability mass. Take it, mass is conserved. So in physics, mechanics, conservation of mass, same thing, you think of it like that in probability space, right? It is conservation of probability mass. And probability mass because I'm integrating density to calculate volume, so in that sense. Okay, so it is just like conservation of mass, but in for probability. No, it holds, that's a property. It's not that it's hold and you can transform. It will always hold. It's the property of a value of a transformation. There is never that it will never hold. There is a possibility though, but that has nothing to do with this. This will still hold. What if that g function is not invertible? Then you cannot use it in practice, but it still holds. It's just that you cannot use it. The idea of you will see in normalizing flow is to design functions that can be inverted. That's why we also call it invertible neural network. But that constraint is coming because I need to compute this. Me being not able to compute does not mean that the distribution does not exist. It's just that I cannot compute it analytically. And all other distributions do that without using this formula. So they, in that case, you don't need that invertibility condition. Like diffusion. In that case, you cannot use it, but does not mean it does not hold. It does hold. Any distribution can be transformed to any other distribution. This is the basic principle of generative model. If this principle does not exist, the subject generative model will not exist. Because the whole idea of generative model is you generate samples from distribution you can sample from. Example Gaussian. Now you transform those samples through some complex nonlinear mapping so that the final samples after transformation are from the distribution you wanted to sample from, which is the generative model, right? So you are able to now generate samples from the distribution. So this holds not this transformation, but the fact that you can transform from any distribution to any other distribution is the most fundamental thing that has given rise to this field known as deep generative models. Okay. One thing I will ask you to try, although that is in the slides also at the end, take a gamma distribution, okay, gamma distribution, and then define a variable y as 1 by x, where x is gamma. Use this and see what you are getting. Take a gamma distribution, x is gamma, y is equal to 1 by x. Now do this business and see what you are getting as the distribution. Okay, you can try it. You will see that you will get inverse gamma distribution. Inverse gamma distribution is the inverse of gamma, and you will get it if you put y equal to 1 by x. There is one more. I think some of you took my reliability course, right? So y is equal to x square. If x is Gaussian, do this, you will get the chi-square or chi-square distribution. So because if x is Gaussian, x square is chi-square distributed, you will get that. So using this, actually many other distributions have been developed. Okay. Any question? Because this is very important. Hmm. No, no, no. It was developed by statistician, and statistician and mathematicians, they work in the abstract space that what will happen. Can we transform this? It came from the basic curiosity. There's nothing to do with data, nothing to do with machine learning. Later machine learning researchers, scientists realized that that has huge application in this domain. Just like the story of laser, right? Einstein developed that with no application in mind. But later you find out that it has huge application. So that's why basic research is also very important without a goal. Although nowadays we are losing it, but it's very important actually. You never know what the application is. And in most cases, the application become prominent much later. Many times after the scientist has died. I mean, Newton developed this GMM by R square and all of those things, right? Was he thinking that we'll use it to send a spaceship to space? No, right? He did not consider sending rocket to space. He developed, discovered, whatever, just to understand the science and the world, right? But later we found that there are many actual applications. And that's actually the basic difference between science and engineering. Science is about understanding the world around us. Engineering is about using that understanding to change the world around us. Right? If you think y is a g of x. So y and x are variables here. No, no, no. Y is x is a random variable. That's why you are saying, right? Here I am applying it on the samples of the random variable. So the transformation is being applied on a random variable. You are right, but it is actually applied on the samples of that random variable. I understand, because random variable is a function by definition. From there you are saying, correct, right? But yes. Yeah. Diffusion will come later. So let's not go there. That's we have 10, 5, 6 lectures for that reserved. But the mapping there is not one way. My mapping is two way. So you can always learn, like you can learn this mapping from y to x, you can learn from x to y also. That's what you are doing actually. Okay, let us come back. Let us talk about the MLE. That is the last thing almost, because central limit and law of large number will take me 2 minutes. I'll just state them. Okay. So maybe I'll show them, not even state them. So let us talk about the MLE, right? From last time. Do you remember what is MLE? Maximum likelihood estimation, but If I have to write it in mathematical term, you remember? If there is something unknown, I can maximize the likelihood of the data, and whatever is unknown, I can find it by maximizing the likelihood of the data, right? So if I write it in mathematical term, it was theta star is equal to arg max theta probability of d given. This is the problem statement of maximum likelihood estimation, right? I think I wrote it yesterday also, if I'm not wrong, in the practical, right? But obviously last time I told it verbally, that the train example, right, from there, right? So now let us see how to apply it for a small problem. Okay. So let us take a problem of coin tossing. So I have been given a coin, and I can perform experiments. That means I can toss the coin and I can see whatever I want to see. By tossing the coin in number of times and by observing those things, my objective is to find out what is the probability of success, which in this case is probability of getting a head. That is my objective. And if I can find it, I know 1 minus that quantity will be probability of tail. That's fine. So the problem statement is, given a data set which is n tosses of a coin, I want to find out what is the probability of getting a head using this principle. Okay. The common sense answer, you'll count the number of heads and divide it by total. You know that, right? But what will this thing give? Let us try. Okay. Will it give the same thing, something different? If it is different, why is it different? If it is same, that's fine. But if it is different, why is it different, right? So the problem statement is, given D, which is my data, and the data looks something like head, head, tail, head, tail, tail, I don't know, and it can go up to n times. So given a data set like this, so I have tossed the coin n number of times, I have observed this data set. Okay. Find probability of head, which is equal to P, which is equal to theta. The problem statement is clear? Any doubt in the problem statement? No, right? Okay. Now if I have to find it using this thing, right, I need to first know what is the probability of data given theta, right? That's what I want to find out, because if I know that, then I can maximize it and find out theta, in theory at least, right? So can you tell me for this problem what is probability of data given theta? Okay, let me ask one more question. So I toss the coin first time. Let's say my outcome is, I'm calling it x1. I toss it the second time. I'll call it x2. So x1 and x2 are two random variables, right? These two are independent or dependent? Dependent? Independent, right? What I observed in the first toss is independent of what I will observe I toss it the second time. So this n experiments are independent, right? You agree? So that means this I can write as product of I equal to 1 to n probability of xi given theta, right? Where x1 is the outcome of the first experiment, x2 is the outcome of the second experiment, xn is the outcome of the nth time I toss the coin, right? Now these are independent. Do you think the distribution will change? Or rather, let me ask you, what is probability of x1 given theta? What is the distribution? Binomial or Bernoulli? I hear two things. Bernoulli, because we are interested in the outcome. We are not interested in how many heads or tails we are getting. Always keep this distinction. What are we interested in? Are we interested in whether we are getting head or whether we are getting tail? If that is the case, it is Bernoulli. or are we interested in how many heads are we getting? And we does not worry about where we are getting the head. So binomial will not make a distinction between head, head, tail and head, tail, head. Binomial will say 2 and 1. Bernoulli will make it distinction because there are 3 Bernoulli now and it will do one at a time. So this is Bernoulli, right? Probability of x1 given theta is Bernoulli, x2 given theta is also Bernoulli. So this x1 to xn are not only independent, but they are also identically distributed, which means they are all Bernoulli. And not only that, the parameters are also same because it's the same coin. The probability of head will not change if I toss it first and second time. My result estimate can change, but the coin will not become biased or unbiased depending on whether I've tossed it 5 times or 5,000 times. The coin remains as it is. It's my estimate can be wrong. Correct? For example, I toss the coin 5 times. I get 4 heads, 1 tail. I can say the coin is unbiased. But I cross the coin 5 million times. I get 2.5, 2.5. Now my answer becomes it is unbiased. My results have changed. My estimate has changed. The coin has not become from biased to unbiased. The coin is what it is. Right? So this theta, original value will not change. So that's why these are known as IID. And this is a very important assumption that you will see throughout any machine learning course you take. That we assume the variables to be IID, which means independent and identically distributed. That's what IID means. Okay. So these are IID, and you said they are Bernoulli, which I agree. So I equal to 1 to n p or theta to the power xi 1 minus theta to the power 1 minus xi. Right? Now, if I take this product, I mean, can you tell me how can I simplify this? This is my likelihood, by the way. I need to maximize it. We'll do that. One is log. If I take log, what will happen? Correct. And what will I get when I take log? There is xi. What will happen to that I? I mean, I'm log we will anyways have to take, but even before that, I want to do something about that I. Product will be converted to sum, but it will anyways be converted to sum because a times, I mean, theta to the power a times theta to the power b is equal to theta to the power a plus b. That will anyways will happen. So with that, just tell me. We'll do log later. I want to take this product to the power. What will happen? Let's take one example that will help. Let's say I toss the coin 2 times, got head 2 times. First time I'm doing head. So my theta to the power 1, 1 minus theta to the power 0. What will I get? Theta. Correct? I'll get theta. The second time I do it, because there is a product, it's also head, I will get theta. So when I do the product, I will get theta square. Theta to the power 2, I will say. Okay, not square, let's call it 2. Right? Now the third time I do, I get a tail. What will I get? 1 minus theta. The product will give me theta to the power 2 multiplied by 1 minus theta to the power 1. This number 2 and 1, what are they indicating? Number of heads and number of tails, number of success, number of failure. So if I take this product to the sum to the power, what will I get? Number of heads will go in the power of theta, number of tails will go in the power of 1 minus theta. Clear what is happening? Whenever it is a head, you will get a theta. Whenever it is a tail, you will get 1 minus theta. So number of times you got head, it will be theta to the power that number. Number of times you got a tail, it will be 1 minus theta to the power that number. So this thing will be converted to theta to the power number of head 1 minus theta to the power number of tail. If you take log also, then same thing will only come. Okay. 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 So now we'll take log. So taking log, when you take log, this is known as log likelihood. Log of probability d given theta is equal to nh log of theta plus nt log of 1 minus theta. Okay. This is my log likelihood, log of the likelihood, right? Next, what will I do? Take derivative with respect to theta, right? Taking derivative with respect to theta. Okay. If I take derivative with respect to theta, what will I get? And that should be equal to 0, by the way. Maximizing. So let's take this one. So nh by theta minus nt by 1 minus theta, and this is equal to 0, right? I mean, log of theta becomes 1 by theta, 1 minus theta is also minus n crumb. This implies what? nh times 1 minus theta is equal to nt times theta, which implies nh plus nt theta is equal to nh, which implies theta is equal to your common sense answer. So maximum likelihood estimate in all ways will give you your common sense answer. Your common sense answer that we generally use are actually based on maximum likelihood estimate. Okay. And that we also saw last time, right? What mode of transportation we take. And without doing any maths, you said that, and I said that that's what the brain is doing in some sense. Okay. Any doubt? Any question? No? This is fine, right? So this is maximum likelihood estimation, and in many cases you will see we will use this in generative models. So this is again very important, because this one and the previous one will be directly used. Even the Gaussian one, many properties will be directly used. The ones I was doing before that was only for building your foundation. But these things will have direct application. So now we are in place where we are discussing things that will have direct application in different generative models we talked about, right? Okay. So yeah. Second derivative. Do it, you'll see. Do it. It's a concave function, so that's why it's the maximum. Okay, you can take the second derivative and see less than or less than, you'll get that. Okay, that's fine. Okay. So for concave function, you only get a maximum, right? So in that case, the actual question will be that for a real problem, this will give multiple minima, and then you will not be able to solve it analytically, and so then you don't know what you are getting. So that is what will happen in reality. But this is a concave function. If you take a negative, that will become a convex function. And in that case, we were getting a minima, because negative log likelihood is to be minimized, log likelihood is to be maximized. Okay. And in fact, negative log likelihood is what we generally work with, by the way. That's what we generally work with. Okay. So now the last two things we'll talk about. Maybe I'll show you the slides. That will also help me show you the KL divergence also, which we'll need. So 30, 50, let's go to 65. Oh, I went to a nice place. Yeah. So this we have discussed, by the way. Remember? Transformation of distribution I was saying for multivariate case. univariate case is here, multivariate is here. So whatever I'm talking about, you will get more of that in the slides if you read it, right? Law of large number, right? I don't want to write, so this one is coming. Even this slide is not coming, right? So that is the problem with the connection. Then it has nothing to do with this. It is a problem with, I think, most probably this landware. Okay. Okay, that's fine. So yeah, suppose I have n variables, right? N variables that are IIDs, identically and independently distributed, right? And each of that variable is having some mean mu and variance sigma square. And this mean is obviously finite, variance is also finite, it's not infinite. Now using these n variables, you can define a variable x n bar, which is the mean of this, right? You can define a x n bar. Don't look at the other two equations, just look at the first equation. So you can define a x n bar like that, right? Which is the mean of this. Now the law of large number states that this sample mean n, right, will be equal to your original mean as this, or will approach your original mean as this number n goes towards infinite. So we have n samples, each from distribution, each of that is now Gaussian distributed. You take the mean, this sample mean will be equal to your original mean of the, which is mu, or will approach your original mean as your n goes towards infinite. This is known as the strong law of large number, which is the second one, right? The weak one is also the same, but it's a more mathematical way of writing it. It says that weak law of large number is in terms of probability. You can see probability that x n bar minus mu, the absolute value of that will be less than some very small number epsilon that is equal to 0 for all epsilon, and then there is something that is to be written, I have not written, almost certainly, almost surely. So this almost surely is a term that is used associated with this kind of things in mathematics. But for our case, what we need, we know that if we cannot compute the expectation, I will take sample and that is what I will calculate the mean and that is my mean. The utility of law of large number for us is that whenever we are in a position where we do not know the exact distribution, I will draw a sample from the distribution, I will calculate the mean and that mean will be my mean that I want to work with. That's what we will be doing throughout this course. The utility is that in many cases you will not know mean, but you will have samples, calculate the sample mean and that is your mean. At least that mean will approach your actual mean asymptotically. Okay? Any question on law of large number? No, right? Okay. So then parametric and non-parametric I was saying yesterday, right? So yeah, that is there. The last thing is central limit theorem, and this is a very interesting thing. And this is actually what justifies in some cases using Gaussian. If you have n variables, right? And these are IIDs. Now these n variables are IIDs, but they can have any distribution. Just they have to be the same distribution with same parameters. They can be uniform or whatever. So you have n variables, they are IID. I'm not specifying which distribution they follow, right? Then the sum of this or the mean of this n variables will give you a variable. That variable will follow Gaussian distribution as long as this n is sufficiently large. I'll repeat. You have n variables and these n variables are IIDs. They can be any distribution, but they have to be IID. For example, they can be uniform distribution. If you take n such distributions and sum them up, or n such variables and sum them up, you will get a n plus 1th variable or a new variable. That variable will be following a Gaussian distribution as long as this n is sufficiently large. And I think I have an example, yes. So what I did here is there is a code also, but take uniform distribution. If you take uniform distribution, one variable, how will it look? the first plot. Take two variable. How does it look? It is already starting to look like some Gaussian. Take 10 uniform variable. How does it look? 10 is that large number in this case. It has already become Gaussian almost. Make it 100, it will be exactly Gaussian. This is the central limit theorem in action. Now, why is it important? In many cases, we assume our data is noisy. And noise comes from several factors. If we assume that it is coming from several factors, but all those several factors are IID, then my noise becomes Gaussian. This is the reason in many cases we assume noise to be Gaussian. But in reality, they might not be IID. And if they are not IID, then it's not Gaussian. So Gaussian is still an assumption, but it at least has some justification. Let's put it that way. Okay. So this is the law of large number and the central limit theorem. Let me discuss one more thing. Okay, this is a very interesting problem. How can you use or compute? Yeah, this is one more thing. I'll stop here. So we will be dealing with distribution in this course, right? Now, if it is points, you can find out distance. But how do you find distance or some pseudo distance between two distributions? There are different metrics for that. The most popular, the most used metric is the Kullback-Leibler divergence, which basically gives you a metric which measures, I will not say distance exactly, but some pseudo distance between two distribution. Okay, and it is generally Kullback-Leibler the divergence between P and Q is integration of P log P by Q. Okay, where P and Q are the two distributions, which is what is shown here, right? There is a negative sign outside, so you see the opposite of what I said. If you take the negative side inside, you will get P log P by Q. Okay, this is the Kullback-Leibler divergence. You can check if P is equal to Q, log 1 will become 0, so you will get that value to be 0. And this quantity is always greater than or equal to 0, you can prove it. So but it is not distance because it is not symmetric. Kullback-Leibler the divergence of P and Q is not equal to the divergence between Q and P. And that is obvious. You put P and Q and P, you can see it's not symmetric. And because it is not symmetric, you cannot call it distance, we call it divergence. But this is the single most used distance metric, pseudo distance metric, whatever you call it, in machine learning, in statistics, and also in generative model as a result, right? We'll be using this throughout this course. Mostly we'll be using the reverse scale divergence, Q and P, but there is application of forward as well, is P and Q. There is a set of algorithm known as expectation propagation, which is based on the forward one, which we'll not talk about, but it's there. There are other divergences also, which are probably better but less used. Like alpha divergence is there, and there are others also. Some of those divergences are actually symmetric, but this is what is mostly used, and this is what we will be mostly using in this course. Symmetric means distance from A to B is equal to B to A. You exchange P and Q, you should get the same result. You exchange P and Q, will not get the same result, because the outside there is a P and then that will become Q. You will not get the same result. So it is okay. I think it is not shown in this slide, so I will ask you. Yes, so there is a difference in the final result you get actually. So when you do Q and P, so suppose I have a okay, let's take P and Q. Let's assume that P is a bimodal Gaussian, whereas Q is a unimodal Gaussian. So now Q can never approximate P, right? So if you take the forward one, which is P and Q, P is multimodal, right? Remember that. Then the Q you will get, the best Q will try to cover both the masses. So it will be a single peak in between where there is no peak, and it will cover the whole probability mass. Okay. So it is zero avoiding. We call it zero avoiding. because P is non-zero, so it will try to avoid 0. Whereas if you do Q and P, opposite, like reverse scale divergence, then it will capture one of the modes and be happy with that. One of the modes it will ignore. So if I have to draw it, I was in this slide, I guess. How can both the modes be super? Well, let me draw it. I think that will become. So when I'm saying that, let's say my P is something like this. This is my P, PDF, mixture of Gaussian. This is what it is. You cannot change it. And now you have a Q. This Q can be changed. You are trying to minimize the KL divergence so that Q matches P to the extent possible. Okay, so what will change? Parameters of Q. Okay, the distribution cannot change, it is Gaussian. Only the parameters will change. So let's do two things. One is you will do KL of P and Q. The other you will do KL of Q and P. And you will minimize both to find out the parameters of Q. Parameters because the distribution should not change. If you do the former, P and Q, if you do this, this will become something like this is what you will get. It will try to cover both the masses. Wherever there is, that's what it will try to cover. Okay. If you do this one, remember this is a optimization problem you cannot solve analytically. You have to do iteratively. Depending on from which initial condition you are starting, obviously, you will probably get, you will either get this, if you start from somewhere this around this, or if you start somewhere from this, you will get the other one. But you will only capture one of the modes. And the reason is very simple, and that was the question I was going to ask. It was not there actually. So the expression of KL divergence that you see at the top, right? Can you imagine as it as an expectation? It is expectation of what? With respect to what? It is expectation of log P by Q. With respect to which PDF? P. That's the forward one. Because it is with respect to P, it is covering a whole mass. That's why you see the mean is shifting to the middle. Right? Do the opposite. Q and P. It is expectation of log Q by P. But with respect to what? Q. So what you will assume, it will be based on that. And that's a Gaussian. So whatever it sees the nearest Gaussian, it will pick. So one is 0 avoiding, one is 0 approaching. That's what you call it, right? So in that sense. So some of the positive masses, it will make it 0. Okay. Fourier transform. Why will you do it? No, no, nothing like that. There is nothing Fourier transform here. It is just that it is known as variational approximation. It's variational inference, to be very honest, where you don't know the original distribution, you cannot work with it. You take a simpler distribution and try to match the simpler distribution with the original one. Fourier is expanding your function into some basis. Here you are not expanding in basis. Here you are assuming something, which I am calling variational, and trying to vary the parameters to match it as close as possible to what is the actual case. And for the actual case, you do not know this, by the way, you will have only data. Okay. So we are done with prob and stat review finally. Okay. Yeah, this is also there, you should study, but this will come later anyways. Yeah, more or less we're done. We're not saying KL is the cross entropy. You get cross entropy as a from there. So see, look at the blue term, that is the cross entropy term, which is coming out of the KL divergence. But there is one additional term also. Okay. Yeah. Right. One example is here actually. I think that's what I told you to do, right? It is here. It was later, right? Yeah. No, it is before. Here. And look at the below, there is a gamma distribution example. An example, right? You see? More like a where you will like to transform distribution. So it's very simple. Suppose you're from mechanics, we'll understand mechanics example, right? So let's take a beam. Let's assume my EI by L square, right? I mean 12 PLQ. Let's assume my L is my random variable. There is a cantilever beam. I want to find out the deformation, right? What is the deformation? PLQ by 3 EI. L is random. And you know the distribution of L, right? What is the distribution of del deformation? You have a L cube function now. So you need to go through it to find out the distribution of deformation. So think of P, I mean, you know, PL cube by 3 EI is the deformation, right? Now L is random following Gaussian variable. What is the distribution of P? Not P, deformation delta. Okay. It will not be Gaussian obviously because there is L cube sitting there. So, but others are constant. I'm saying only L is random variable. L is Gaussian. So it will be delta. Understand? So in real life, we often deal with random variables where we know the distribution. At least we have some estimate. But then those random variables are goes into some nonlinear function, and we are interested in the output of the nonlinear function, right? So in that case, we cannot do that without this. So PLQ by 3i or whatever I'm saying, this is a very simple mechanics, first year mechanics, right? Not first year, second year. I mean solid mechanics 104. So second year example you can think of, but this is applicable to anything, right? I mean any nonlinear example, kinetic energy half mv square. I know the distribution of V. What is the distribution of kinetic energy? Right? So even for linear this will hold, but for linear it's very simple. You don't need this. So I'm not saying, but even for linear, right? Force is equal to mass times acceleration. Mass is Gaussian, acceleration is Gaussian. What will be the force? What is the distribution, right? And if you know the distribution of the force, you can now operate on that and take informed decision. You'll be taking informed decision. Right? So in that sense. Okay. Okay. Thank you. तो आज का वीडियो का रिकॉर्डिंग क्या मिलेगा मुझे पता नहीं, ठीक है देखेंगे कुछ प्लान है मेरा पर देखते हैं क्या होता है।